So today we have Erik Papp from Groningen in the Netherlands, and he will talk about the unified parallel transport descriptions of non-cyclic states, exceptional points, and complex geometric phases. So whenever you're ready, Erik, go ahead.
Yeah, so, well, thank you all for coming. Thanks to the organizers for giving me the opportunity to speak, and also welcome to those who will be watching this later. So yes, I'm Erik Papp, and I've been doing my PhD research together with my supervisors Daniel Boer and Holger Waalkens, and I hope to defend this coming October. And so the main results of this research, that's what I want to talk about today. And so yes, I submitted a long title, but the advantage of that is that you know basically all that I want to talk about. So there are various effects, phenomena in adiabatic quantum mechanics, and for this we want to have a unified parallel transport description. So let me first go into an introduction on geometric phase and parallel transport, and then discuss how the talk will be like. So there we go. Click here. Yes, it works. So of course there are the main papers from around 1983. So Barry's paper where he demonstrated the existence of this geometric phase. So if you adiabatically evolve an eigenstate, it gets a dynamical phase, but on top of that, a geometric phase, which is only dependent on how you walk around. And then readily afterwards, Simon found that you can view this as a holonomy effect, and this gives you this picture. So you get a time-dependent Hamiltonian by varying system parameters. So you start at this point and you come back at it. You have to avoid degeneracies while doing so. And then, well, you have the energy bands of the Hamiltonian, so your upper and lower one. You pick your energy band of interest, in this case, the lower one. You have an initial state, and then you can drag it along, and it comes back with a rotation, and this rotation angle is exactly the geometric phase. So this is the standard theory for Hermitian Hamiltonians. In the non-Hermitian case, we get an additional effect, namely that of non-cyclic states and exceptional points. So let me illustrate that using the standard EP2, by which I like to refer to this particular system. So X is now complex, this Hamiltonian is non-Hermitian, the eigenvalues are generally complex, and so we can have more intricate topology. And we see that the energy sheets of surfaces now interconnect. So if I now follow this loop, then I see that my initial energy does not return to itself, it becomes a different energy. And so this again gives rise to non-cyclic states, because if I would follow an initial state with this particular energy, I get an eigenstate with that energy, and hence they are in different rays in state space, and hence this is known as a non-cyclic state. And of course, the degeneracies that are responsible for this behavior, these are known as exceptional points. So now you may ask, how can we do this in a parallel transport way? Because, well, you see this picture, you're going to see this picture more often. It doesn't differ that much from the previous one, so can we again do parallel transports? And so let me then list relevant works on this topic. So of course, I start with the seminal paper by Garrison and Wright from 1988. And there they demonstrated that also in the non-Hermitian case, you can get some kind of geometric phase, because you can replace the brass by left eigenstates, and you can repeat the adiabatic argument, and you can find a geometric phase in case this blue curve describing change of energy does end up at itself. So you can again do this rotation trick, you will just get a complex valued phase. So much later, we find one of the first parallel transport models behind this, with a paper by Mehdi Nafi, Mostafa Sadeh. And there they have some kind of multi-bundle approach for this phase. So what they do is not this picture, but kind of the idea is that you can cut these energy bands again. So like you can like cut them like this. So you can have like a lower and an upper one. And if you then do the transport, then this part you do in the lower bundle, and this part you do in the upper bundle. So this was really on the phase. Concerning the non-cyclic states, I feel there have been multiple papers by Chion, Tanaka, and sometimes a third author. And there they studied what is happening, usually using projector. So they did this with block states, for example. But then still the phases were not in. And so this is really the gap we wanted to fill. Like we wanted to have a single bundle approach that can incorporate both this generalized geometric phase and the swaps which happen around exceptional points. And I'm very happy to report that we found such a method, and this is basically what I want to share with you today. So how do I want to do that? Well, I always like to start with just focusing on the topology. So we're going to first study the energy bands and exceptional points, because then the geometry will be built on top of the topology, and so the geometry will be 2, 3, and 4. So I will just start with, well, the most important space that we use there. It's a bundle of eigenstates in some different way. And so I claim that on that you can model adiabatic evolution, in particular non-cyclic states. So this will be non-standard. So I want to give special attention to that. And at the end, I want to end with a note on the quantum geometric tensor. I know some of you are working on this, and I really feel that this theory can help you, because we will find this eigenstate bundle will actually be a natural home for this tensor. Okay, let us then get started with the topology. And for that, well, I have, again, this picture. And so the first thing I want to talk about is how you get this instantaneous energy changing in time. So this function E of t that you use in the dynamical phase, and hence in the derivation of adiabatic dynamics. So very often this function is just assumed to exist. So given a loop in parameter space and given an initial energy, I get this function E of t. But formally, you would have to prove that this exists. And in doing so, we will find exactly what we need to study exceptional points. So I hope I can convince you that this is like a lifting problem. So there's the path, here's the initial condition, and this is like the solution. And hence, we can basically use standard results from covering theory once we show that these energy bands form a covering space of the parameter space. And so to do that, we need to be a bit more formal. So the space of non-degeneracies, I like to write NH. So these are all x in the parameter manifold for which hx is non-degenerate. And this means that hx has n different eigenvalues, where n is the finite dimension of the state space. So then what is the bundle on top of that? Well, there are various ways of arriving at this. So from this picture, you see that above every non-degeneracy, you should attach all the energies of that Hamiltonian. So to each x, you attach spec hx, or you view this as graphs, and then you get all tuples x, e, such that E is an energy of hx. So we now have a formal statement we want to prove. We want to prove that spec h is a covering of nh. And to do that, it's most convenient to get the Hamiltonian out, actually. So in general, this can be any parameterization. It can behave in all kinds of ways. So you don't want to deal with that. And you don't have to, because we can focus just on the vector space itself. So just the state space, which is a complex vector space. I don't assume it to be equated with an inner product. We can define like a non-degeneracy space of it, which I like to call NV. And these are all operators on V that are non-degenerate. And then we go to the spectrum bundle of it. And well, as the name says, this is the bundle of spectra. So to every operator, you attach its spectrum. And so you're going to look at this simple combinations, operator, comma, eigenvalue of that operator. So to show that spec V over NV is a covering, it's much easier to do. And so either you can reason using the characteristic polynomial, or you view this as an implementation of an even more simple geometry that we found recently. But just to say that it's very nice to prove that spec V is a covering over NV, which I will not go into detail now. But once you have this, it's easy to prove the covering property of spec H, because we can use the standard technique of pullback. So the projection we want to show to be a covering is now the pullback of a covering along the Hamiltonian map. So you send a parameter to the operator corresponding to it, namely the Hamiltonian. And so this result tells us two things. So the first thing is that spec V is now like an abstract model space for the energy bands. So it's like a kind of a classification, because if I have a specific Hamiltonian, I just have to read out this specific space. The other advantage is that if you prove the covering property this way, then you get the covering property for any continuous family H. So I don't need to make any reference to H being Hermitian, PT symmetric, anything, which I think gives you a very firm and general background. Okay, this proves the covering property. Can we then actually use it? I see someone raise their hand.
Eric,
Yeah.
You said that this is completely general, but I presume you're going to talk about exceptional points later. But
yes,
the number of energy eigenstates is not complete. So where in this diagram in equation 6 do you encounter the completeness of the energy eigenstates?
That's here, because we only claim the bundle property over the non-degeneracies of the Hamiltonian family. So indeed, if you would come with like a pathological example of a constantly degenerate Hamiltonian, then this space would just be empty. And so there's nothing. So yes, so things can go wrong, but then it's kind of obvious. And
what do you mean by degenerate? I mean, degenerate means two eigenfunctions that are orthogonal that describe two energies that are equal.
Well, by non-degenerate or by degenerate, I just mean if you, well, basic idea, if you just write it as an n by n matrix, then this does not have n distinct eigenvalues. That's the only thing I assume. I don't assume anything on orthogonality or so.
The n by n matrix does not have n eigenvectors.
Eigenvalues.
Eigenvalues, well, the secular equation has n solutions.
Yes.
It's an nth order polynomial.
Yes, and so we assume
what's missing is the number of eigenvectors.
So yes, that's the second thing you could ask for, but we only ask for that all the eigenvalues that you get from this equation, so these n different values, that these are all distinct. So all multiplicities are 1.
Oh, okay, good.
And so indeed, you can also go to eigenvectors, and then you get this difference between non-degenerate and diagonalizable. And then you can go further to Jordan blocks. But so we only need to stay within the special class of non-degenerate systems, also for the upcoming geometry, which will not hold for diagonalizable operators, only non-degenerate ones. So does that answer? Sorry?
Yeah, I mean, but you know, I mean, there are perfectly normal Hamiltonians with degenerate eigenvalues.
Yes.
Are they not in this category?
Well, you can. I would say if you have like a constantly degenerate system, I would hope you can like separate them still into two non-degenerate ones. And well, for most examples, I would say non-degenerate is enough. Also, because you can prove that non-degenerate, so NV is open, is a dense subspace of NV.
Okay, I'm sorry I'm asking so many questions, but
no.
I did not think that the Berry phase that's derived in Hermitian quantum mechanics required that energy eigenvalues be non-degenerate.
Yeah, so this is one of these details. So if you have adiabatic theory, you go through degeneracy, then at the degeneracy, your eigenstate would become a superposition. And so after the degeneracy, you would have then the energies are no longer different. So like you have one coming and then that splits into two. You have like a quantum superposition without a definite energy. So you cannot talk about instantaneous energies anymore. And so, yeah, this is kind of hidden, but you need this non-degenerate assumption, even in the Hermitian case.
Well, okay, I mean, so the whole Berry discussion actually has an implicit assumption on non-degeneracy.
Yes.
Is that widely known?
Well, there's the Wheelcheck-Zay paper. They looked at the degenerate case. But if you look at this paper, what they basically tell you is that the Berry argument splits over the degeneracy subspaces.
Oh, okay.
So you get like one argument, a UN argument for each subspace of dimension n. And so in the case you just have non-degeneracy, everything is U1, everything is a phase. But even in the Milchek Z, you want these different energies of the different subspaces also to be distinct. Like, yeah, we will see why, because this will actually give you the singularities of the space we will see in a moment. So, but please ask these simple questions, because I feel like sometimes things go wrong exactly because these simple things are misunderstood.
Okay.
So, yeah.
There's another question. May I ask this question? It's Uwe
Yes.
Günther. Yes, you are using here the notation of spec, this well-defined notation in algebraic geometry as a prime ideal. Does your notation have something to do with this theory, or is it just an ad hoc definition that you are using here?
Well, you kind of can say that we use algebra in a different way, because you can say like, well, spec A is the zero set of characteristic polynomial where A is fixed. But like well, if you have like a determinant of z identity minus A, this depends on both Z and A. So if you fix A and look at the zero set, you get spec A. But if you vary both of them, then you actually get this space. So
yes, so it's an ad hoc notation that you are using, because there's a standard notation which is completely different as prime ideal in Ital cohomology. So it has nothing to do with these things.
No,
you're just using this.
We're not using that. The nice thing is that
yeah, well, because it might trigger a big mess here in this context. Okay, thank you anyway.
Yeah, maybe. Like I also know about spectral geometry, which is like also a term in differential geometry, and we're also not doing that. But I guess, well, if you have spectrum and geometry together, then well, there are all kinds of things you can do. But okay, well.
Oh, okay, thank you.
Yes. So, well, we just proven that spec H is a covering. How can we use that? Well, we can use a standard concept from covering theory, which is known as the monodromy action. So, in case you're less familiar with this, if you look at this loop here and this initial point, then the endpoint here, like this does not depend on the exact shape of the loop below, but we are allowed to deform this a bit if we just keep this base point constant. So imagine we would change this more like into an ellipse. And then this loop this path will be also a bit more stretched, but the endpoint will be the same. So this is a standard result in covering theory. And I would say the nicest way of writing this is to say that there's a monodromy action, because, well, as we only are interested in the deformation class of this loop, and so the deformation classes form the fundamental group, you can say like, well, the class of this group acts on this point by transporting it there. So you get like the class of gamma times an initial point in the fiber is the endpoint. And so this is known as the monodromy action of a covering. So now I just use this picture to explain monodromy action to you, but you can also, but I just used the same picture to explain like exceptional point permutations of energy. And so really there's a tautology between these two, like studying these permutations and studying the monodromy action on spec H, which I think is nice. So here I say that we are not the first ones to see the relevance of the monodromy action in this. So also Tanaka and Sion had work on that. But as far as I know, we are the first to really formally prove that the space is a covering, and also we get kind of like the minimal space that you need for it. So now I see another hand.
Yeah, sorry, I just want to make clarifications. In your plot, the vertical axis is the real part of the energy.
Yes.
So which energy did you choose? Is it ground state or?
No, all the states are there. So like, so if you have non-Hermitian systems, there's not really a global ground state. So you can here say like, this is the ground state and here's the first excited state. But well, essentially we are looking at all the energies of the Hamiltonian. And so this would indeed be complex values. And so
but for finite dimensional case, you have discrete spectrums.
Yes.
Is that right?
Yes.
So that plot a surface.
Sorry, that you get the surface by looking at the energies for different parameter values. So for this parameter value, I get a Hamiltonian operator. finite dimensional, so I get these two energies. Then if I go to, well, a nearby point, for example, here, I get an energy there and I get an energy there. So like the band property, like it's like in condensed matter where you have like a wave number appearing.
Okay,
So,
thank you.
yeah.
Thank you.
Okay. Yes, so now we have the non-Hermitian action. You may still say like, well, it's a bit abstract. Can I actually use this in practice? And well, the answer is yes. And so it helps you when studying the permutations due to multiple exceptional points. So the problem is a bit like this. So we have here two exceptional points. We can encircle both of them separately. So we get some permutations. And now the question is, how do we get the permutation of this big loop encircling both of them? So we found around 2017, 18, that this was not known in the literature. There were even some papers claiming that this was ambiguous because you don't know which of these two permutations comes first. And so that you couldn't calculate it, but essentially you can. And the Monodromy action tells you how. So first, this picture is not really honest. Like you may have this mentally in your mind, but if you want to compose permutations, you should talk about the permutations of one and the same reference spectrum. So you should fix a reference point, for example, just a point here in the middle, and then make sure that all your loops start at this point. So you should deform your loops to get a picture like here. And then it follows from the fundamental group that now the class of the big loop decomposes into the classes of, well, here gamma 1 and gamma 2 in a particular order, depending on how you, what your direction of traversal is, etc. And so this means that the fundamental group tells you which of the two comes first, and that means you can calculate the permutation due to the big loop gamma. So yeah, indeed, the Monodromy action can help you in practice. So the final property of the final use of this, of having this formal background of spec H is when we look at definitions of EP. So when I started as a master student, I found like these many characterizations of exceptional points, like all the way from Cato's original book to, well, just branch point singularities to more. And so we looked into this, and well, if you go into the details, really many of them are inequivalent. And so this is also something I want to briefly touch. So I would say, looking around, the most popular definition of an exceptional point is the coalescence definition. So you say X naught is an EP if Hx naught has coalescent eigenstates. In other words, Hx naught does not have an eigenframe. And here I just look at the finite dimensional case. So it's clear from this definition that it is inherently point-like. If I know that X naught is an EP, I still have no real information on a neighborhood. It may very well be that, well, there's something happening at X naught and around it, nothing is happening. While on the other hand, for some exceptional points are of course the swaps. And so these swaps was what I would say the most, well, is one of the other famous characteristics of exceptional points. In fact, the first confirmation by Dembowski et al. Really focused on having these swaps and not the coalescence. And so we were like, well, maybe you can put this at the center of the definition, and using topology, you can. So if you just look at EPs from topological viewpoint, there's something nice you can say, namely spec H is usually not trivial because of these sheets interconnecting. And we can now say like, well, the degeneracy is an EP if it is responsible for, well, part of the non-triviality of spec H. So usually you cannot say where a bundle is not trivial, for example, the Möbius band, you cannot say where it twists. But because the non-degeneracies and the degeneracies are together in the parameter space, you can still attribute non-triviality to degeneracies in, well, a straightforward way. And you can check that for basically any non-pathological system. This is equivalent to requiring that swaps of energies are possible arbitrarily close to the point, or you take this multivaluedness viewpoint so that some of the energy bands, they are not a graph of a single valued function. So resuming, I would say, well, you have the coalescence idea, you have this topological idea, and that these are, well, interesting for their own reasons, and it would be nice if you can really distinguish what is what. Okay, but this is my final note on the topology, so let's now continue with the geometry. And so for that, we need a new space. It will be the eigenstate bundle. And there are multiple ways of arriving at it, but let me just share our original motivation. And that's on this slide. So we start top left. So original motivations were local eigenstates. And by this, I mean eigenstates which are parameterized by system parameters such that psi of x is an eigenstate of hx. So please note that I do not require psi to be normalized or anything. Like I don't have an inner product, so I cannot even define normalized. I just want psi to bend smoothly on x, where x is defined, of x is taken in some open subset of the non-degeneracies. So the reason you want to look at local eigenstates is if you want to write something like the Berry potential or the Berry curvature, you get like derivatives of psi, and these derivatives only make sense if psi depends on x. So in other words, if you want to do anything geometric concerning geometric phase, you will be using functions like these. So because of their importance, we were like, well, what's now a natural home for these? So written like this, it's clear that they would really fit the language of local sections of some projection. So then we need to find the right total space for that. And this we like to call Eig-H. And so how do you get it? Well, you can say like, well, I'm going to look at all the graphs of these. So then I'm going to look at x, psi, where psi is an eigenstate of hx. And so it will have some definite energy. And it's very convenient to list this energy because if you need it, it's just part of your input data. There's also another way of looking at it, and that's why we like to call it the eigenstate bundle. So to each non-degeneracy, you attach all the eigenstates of hx. So please note this is not the eigenspace. This is just really the space of all eigenstates. So 0 is not in there, and also superpositions of states with different energy are not allowed because they would not have a definite energy anymore. So, okay, that's the space we are going to use. Well, it's a bit hard to draw this, but well, the picture on the right can help us a bit in understanding its properties. So to this point here, what I would attach is the eigenray corresponding to this point, and you attach the eigenray corresponding to this energy. And so here we find one major challenge, namely that this bundle Eig-H is not a principal bundle like the usual form. And the reason why is that, well, the group here is non-zero complex scalars, like scaling your eigenstate, because if I scale an eigenstate, I again get an eigenstate. But this, the orbits of this action are now the eigenrays. So this is one orbit, and here I get another orbit. But now the group action is not transitive, which means that I can scale this vector as much as I want. I cannot get it to have an energy like this. So these two black arrows are not related by the group action, and for principal bundles, they should. And so this is a point where we really start to differ from what has been done. We really embrace this fact of having a non-principal bundle. And that means we have to look at, well, a generalized version of these. And this we can do in a very mild but successful way. So as I just said, an eigenray is one particular orbit of the group. And so we basically want to say, like, well, now my fiber is not just one orbit, but it's, well, finitely many, which are disjoint. And so this brings us to this slide, namely, so instead of requiring the space to be a single orbit, so this is also known as being a torsor, we require it to just consist of this disjoint union of orbits. And because this is like, well, a direct sum of what's here, we like to call this a semi-torsor, just a name. And so once you define semi-torsors, then it's easy to generalize principal bundles to semi-principal bundles. Namely, these are just bundles of these spaces, and you require local trivializations to be G equivariant. And so please note that if I would remove semi here, then I would get the definition of a principal bundle. And well, I forgot to say, of course, if I just have a single orbit, then that's a disjoint union over just one thing. So every torsor is a semi-torsor, and so every principal bundle is a semi-principal bundle. Okay, so I get a category of semi-principal bundles. That's nice, but can I still do parallel transport on these? And the answer is yes. So you can still make sense of group compatible connections. In fact, if you just write the axioms using the group, you can just copy them verbatim. So then it's also not a surprise that the parallel transport maps will again be G equivariant. Only I will get one major difference, namely because the group action is no longer transitive on the fiber. The holonomy maps need not be translations by a group element. In other words, I cannot represent what is happening by a group element. And this is exactly the case for a non-cyclic state. Namely, the state comes back, but I cannot describe this using just a complex valued phase. Okay, so this sets the stage. Now we want to show that this Eich fits this description. And again, the most convenient way is to take the Hamiltonian out. And we get the eigenvector bundle like of the vector space. Again, this is just picking a name. So similarly, now we, to every non-degenerate operator, attach the set of eigenvectors, which means I'm going to look at tuples, well, operator, eigenvalue, eigenvector. And the claim is that this is a semi-principal bundle. And again, you can check this directly, or you can, well, verify that this is the pullback of something simpler. So recently we found that you can look at directions in the vector space, or like ways in how you can decompose V into one-dimensional subspaces. And this actually also gives you a semi-principal bundle, and this is the pullback of that.
May I ask you a question?
Yes.
Oh,
Oh,
sorry.
there are two.
Yeah, concerning this semi-principal bundle, maybe it's directly related to a semi-direct product of groups. So you have in a group, you have a semi-direct product. Actually, you have a scaling group, and you have just a rotation group. And in this structure, your semi-torsor is operating. I guess is this a guess correct, or is there some?
You are guessing correct. We will see the semi-direct product coming later.
Oh, okay. Thank you.
Yes, it will be there. Yes.
Yeah. Okay.
Yes, there's another question.
I was wondering what is the difference between this semi-principal bundle and bundle over the covering space of the base manifold?
Also, you guessed correctly. You can show that a semi-principal bundle is always decomposable in a principal bundle over a covering space.
Yeah.
That's indeed true. So then you may ask, like, what do you gain from defining semi-principal bundle? And that's, well, there's the technical thing that if you want to lift a path now, then if you lift first to the covering space, then you will not get a loop. So you do not get holonomy when you go around the principal bundle. So you want to go in one go. And for that, you just need a principal bundle. That's the only way to do the phases and the swaps simultaneously. Otherwise, you're breaking up into first the swaps and then the phases.
Yeah. Also, the group is U1, right?
No, the group, we are not requiring normalization.
But it's just one-dimensional, that is.
Yes, the group. So
I see.
Every eigenray is one-dimensional. But, well, we want to have complex valued geometric phase, and the exponent of, well, the whole complex plane is, well, the non-zero complex numbers.
Okay.
So that's what we needed. Yes, thank you. Okay, so we get this space. And so then we still need the connection. We want to walk around in it. And then we notice that, well, if I have such a triple, where A is non-degenerate, then I can find this like left eigenstate or like eigencovector, which comes from the left. It's a functional, and this is uniquely fixed by saying, well, it's a left eigenstate of A with the same eigenvalue. And when it takes on V, it just gives me 1. So this is like a normalization, but this is like algebraic normalization. There's no inner products used here. This is just vector and dual vector. Okay, and using this theta, which we can just freely put in the notation of the point, is fine. We can define the connection. And so, well, what does the group do? The group scales a vector along itself, and then this connection should tell you, okay, how much did you do then? So dv is like looking at how much did the eigenvector change, and then theta reads out how much this is along the direction of v. So really, we are looking at how much v changes along itself. And so in parallel transport, then you just say like, well, v is not allowed to change along itself. And so you can prove this connection is canonical. And now I have to show you that this actually gives you what Garrison Wright did. And then again, we are going to pull back along the Hamiltonian. And so then we get that IH over NH is a semi-principal bundle for any smooth family H now. So again, with this remark that it only works over the non-degeneracies, but we do not need to ask if H is Hermitian, PT symmetric, or anything. And also we get the connection on this space omega H, which is simply the pullback of the abstract connection I just showed you. So now you could say like, well, omega H is what Garrison Wright found, but here I always like to be a bit more precise, because omega H is not a gauge potential. If we want to get that, we have to work in local coordinates. And so, as I said earlier, these local eigenstates are like local sections. So if I have psi of x, then I get a local section, which I denote psi hat. So this basically inserts the local eigenstate, and well, you can then immediately list its energy and its dual and the dual. So this is the left eigenstate corresponding to that. And so if I then calculate the connection in local coordinates, which is a pullback, well, theta becomes chi, v becomes psi, and so I get this expression, which is indeed what appears in Garrison and Wright's treatment. And also, we find the right transformation law, if you view this as a gauge theory, because if I now have different local coordinates, which means I have a different local eigenstate, if I describe the same energy, then these differ by just a rescaling, so position-dependent group element. And so if I then do the calculation again, clearly I also get the derivative of the group element, which gives us the usual additional term for a abelian gauge field. So all in all, we have one of the main results of the work, namely that Ig with this connection omega H really models adiabatic state evolution. So it does cyclic states, non-cyclic states, and you can even put the dynamical phase in if you want.
May I ask an additional question?
Yes.
You are just here considering this semi-principal C upper X bundle here in this way. Why you are not embedding it in just a one-dimensional projective space, so that you can handle also the zero and the infinity included?
Once again, where do you want to have projective space?
Now you have here your corollary actually, and there you have this C. I don't know how it is called. This non-vanishing C actually minus multiplicative C bundle.
Yeah, C cross C times if you want.
But you might just embed it in a natural way in a one-dimensional projective space, in the projective line, so that you can handle also infinities and the exceptional points directly. Are you excluding this explicitly, or
well,
you simply didn't try it?
Well, I guess that C cross here appears in a different way than you may expect, because this is basically just a structure group, right? So
yeah, sure.
I mean, if you have like just an ordinary linear algebra problem, you know that your eigenstate is unique up to rescaling with a scalar. And so the symmetry group is just this group of scalars. And so I just want to stay within.
Yeah, so, but you just may include infinity and zero also in your scaling. So just using a different chart. Okay, so you didn't do it.
No, I think you cannot do zero, because like at least we have the convention that the zero factor is not an eigenvector, and that's, well, what you need to get nice geometry. Otherwise, every fiber has at least 1 point, namely the zero factor. And so to us, it's crucial that the zero factor is not there. So I would say that then zero and its inverse infinity would not need to appear here.
Okay, okay. Mm-hmm. Okay, so, thank you.
Okay, yes. So, okay, I said this, this connection then models, well, cyclic states and also non-cyclic states. Due to time reasons, I think it's best if we focus on just the non-cyclic case, because this really uses this non-standard property. So if you want to discuss more about the cyclic case, well, maybe we can do that in the discussion afterwards. So how do then these non-cyclic states work? Well, then we really need to study maps of semi-torsors. And so, well, this is then a bit non-standard, but you can still kind of phrase a diagonalization result for that. But let me not go into these details. Let me just illustrate what happens for the EP2. So no, there's a parallel transport map. I should tell you, like, okay, on which space does it act and what does it do? So the space on which it acts, this is the set of all eigenstates of the reference Hamiltonian. So for the EP2, I just picked 0 as my reference point. It's a nice non-degeneracy. And so, well, H0 is just diagonal 1 minus 1. So the eigenrays are the eigenray through the two basis vectors. And so please note this is a disjoint union and not a direct product, because again, we are not looking at linear superpositions. These will not have a definite energy, and also the zero factor is not there. So okay, the parallel transport map, or holonomy in this case, is now a map from this set back to itself. And so I should tell you what it does to elements from here and elements to there. And so for the EP2, you can calculate it, and it does this. So basically, you get minus I times the other direction out of it. And so this is the map we're going to study. So what does now this diagonalization tell us? Well, the first step of diagonalizing, also for linear maps, is that you look at minimal invariant subspaces. And in this case, we clearly see that this eigenray is mapped there, and the second one goes to the first. So the whole space is one and the same minimal, it's one minimal invariant subspace consisting of two eigenrays. Then the diagonalization tells us that every invariant subspace has some kind of, well, eigenvalue. It has a characteristic group element. And this group element you can get by applying the parallel transport map as many times as you have orbits. So after 2 times, every state in this union comes back with the same characteristic group element. And of course, for the EP2, this is -1, because if I encircle twice, I get -1. So this idea of having invariant subspaces and characteristic group elements for every subspace, this is what holds in general. So here illustrated using the EP2. Now I can imagine you still say, like, well, this is a bit, well, abstract, a bit weird. Why not use holonomy matrices? These maybe are much easier. So indeed, you can get these, and for that we need some kind of frame bundle approach. And so let me illustrate how you do that. So I'm just going to start simple. Here's a circle, and if I would ask you to draw a circle on the board, well, you would get a piece of chalk and draw a circle. But then in doing that, you had made a choice, namely, you chose the point where you first put the chalk on the board. So you picked this initial point. And of course, it's a circle, like no point is special. You just picked a point in order to get your work done. And this is, of course, at the basis of gauge theory. So now that you know the drill, let us make this a bit harder. I'm going to ask you to draw 2 circles. So what do you do in this case? Well, you just draw 2 circles. And then we see that in drawing this, for both of them, you can pick their own starting point, right? There's no reason why these should be related. However, there's an additional choice you had to make, namely, which one of these 2 circles you draw first. And this is behind frames. If I want to describe this collection of orbits, then there are 2 things I should worry about, namely each orbit I can pick an independent representative for, and then I also have the symmetry of reordering these representatives. So you can, in general, you can define a frame of a group set to be just a set of representatives such that every orbit is represented by exactly 1 point of one of these in the tuple. And so if I now go to the case of eigenstates, then, well, instead of circles, I have the eigenrays. I have to pick a point from each eigenray in some ordering. And then it's not that hard to see that we get the usual eigenframes back. So the eigenframes in the sense of linear algebra. And so, so the frame theory that we did is more general. You can even phrase this as a functor. So it also gives us a natural symmetry group. Namely, it's a Reeve product, and this is like individual. This consists of 2 symmetries, namely individual scaling, so like picking where on the circle the point is, and then also reordering how it is done. And here we get, well, the semi-direct product I promised. So you get these scalings, and then semi-direct product with the permutations. And so for the case of C times, you may be more familiar with this group as the group of generalized permutation matrices. So you say like, well, you pick a permutation matrix, but all the ones can be any non-zero complex number, or you view these as products of diagonal matrices with no zero on the diagonal times an ordinary permutation matrix. So does this now help us to describe the EP2? Well, yes, it does. Because now if I pick E1, E2 as like my reference eigenframe, I can consider what parallel transport does. I get some other eigenframe back, and this then differs from my initial eigenframe by a generalized permutation matrix like this. And so here you get all the phase factors in there. Of course, this matrix is like gauge dependent. If I pick a different eigenframe, then I will get a different matrix. And so here you see the more familiar 1 and -1 phase appearing. So, okay, this matrix is then kind of gauge invariant of a gauge covariant. Are there then also invariants? Well, yes, that's this diagonalization result that tells us that the way in which orbits are commuted, this is of course an invariant, and you get these characteristic phases, and for that you just multiply all the phase factors that are permuted. So these two you multiply, and these two you multiply, and indeed in both cases you get -1. So okay, you can study non-cyclic states using these frames. In fact, you can do even more with these frames, like Manini-Pistolesi found off-diagonal phases. And so also these you can explain. But for that, well, let me refer to papers, or you can ask later. Let me now come to an end with, well, the final note, namely on the quantum geometric tensor. So this tensor was, well, first found by Provoost and Vallée in 1980, but then 1989, Berry found that this was very relevant for adiabatic reasonings. Namely, you get, it is this tensor as appears in his paper. And so its anti-symmetric part is related to the Berry curvature, with which you can calculate geometric phases. And its symmetric part is gives you a metric. But so we now take another perspective on this. And so we start with this operator that appears here. So this is a projection. And so now we note that this projection is, you can get this by looking at covariant derivatives on Eik-V. Let us take Hamiltonian independent perspective. So denoting covariant derivative by nabla, nabla of V, then add some tangent of Eik-V, which I denote by fracture V. Well, this is the usual derivative minus the part that shouldn't be there. So there omega comes in, and because omega is theta dv, I can regroup this and I get like dv exactly altered by this projection operator. You can also check this for theta, you get d theta, and then followed by again this projection operator. And so we find a natural generalization of the QGT. So we write it like this. And so basically what you do, you just combine the two covariant derivatives. So this will again be a vector-like thing, and this will be a covector-like thing. So you can combine them, and it gives you a number. And using this result, you can easily see that it gives you this, which is the natural generalization of Tij above. So from this, we have a few advantages. So one of them is that this nicely shows that also the generalized QGT is scale invariant, because V and theta scale inversely because of this normalization condition. So the covariant derivatives preserve this action, and so these two exactly cancel out the group action. So, well, it's invariant, and you can even reduce QGT because of that to a tensor on just the energy bands, which can also help you out. The other thing is that because we now on Eik-V, we have a rigorous footing now, because these are all well-defined mathematical quantities, so I can be really precise. And I have a Hamiltonian independent perspective, so I can study the QGT for Hermitian systems, PT symmetric systems, what you want. Okay, now that we have this is again an abstract story. Can we be a bit more explicit? Well, yes. And the way in doing this is being a bit more explicit, like how does a tangent of Eik look like? So if you want to do that, well, Eik has operator, eigenvalue, eigenvector. So you should kind of have tangents for all of them, but thankfully we can get away with a little bit less. So in the direction of V, you have like, well, tangents along the eigenway. However, because of scale invariance, this will not contribute. Also, the eigenvalues we did not see appearing, so that is also something we don't need. So the only tangents that we're interested in are those changing the operator, but without changing the eigenvalues. And so, of course, what fits the bill there is similarity transformations. And so given an operator X on V, putting an I there for convenience, I'm just going to look at this tangent, which you get from doing similarity transformation. And so you can check, this is the only part that contributes in the QGT. So like V1 is then IX1 plus things that don't contribute, similarly V2. And then I see that I basically get a bunch of expectation values. So this expectation value of the product minus the product of the expectation values. So as I just said, the QGT is scale invariant. So this is also scale invariant, but still theta and V, they transform. Can we not write it in just scale invariant quantities altogether? And yes, you can. So instead of the eigenvalue, you're going to look at the eigenprojector, so which is equal to V theta. If you do that, you can write this using like well, the trace, this density operator formalism. And so this is another way of writing it. Okay, this gives us then an explicit view on this. So then we can check in what way does this generalized quantum geometric tensor still follow properties of the old one. In particular, do we again get this decomposition into a metric and like the curvature? This 1/2 is just convention. And the answer is yes. So for the anti-symmetric part, well, you easily find that this is the expectation value of the commutator. And that is indeed the curvature. And for the symmetric part, you get some kind of metric, and we even find that this is the form of a covariance. Because, well, you can write it like this. And so you get a symmetric operation where you really have to put this anti-commutator in to get it. And so, well, kind of surprised that we were here because, well, we were not looking into probability theory and suddenly we get a covariance. And so, interestingly, you can also relate then the QGT to the generalized uncertainty principle. You have the usual one, and then you can strengthen it with an additional term. And actually, this relation is like a Cauchy-Schwarz inequality on G. So we didn't expect that, but yeah, it was very nice to find this. But okay, let me then conclude this point on the quantum geometric tensor and just summarize what we've been doing so far. So the main point was to find this formal single bundle approach to adiabatic evolution of eigenstates. And so for this, we found then various parts of it in order splitting like the different physical effects you want to study. So if you're interested in exceptional points and how energies change, well, you can just study the energy bands, which we found to be a covering space. The generalized geometric phase naturally corresponds to the connection we found on Eik. And so this works for cyclic states, but also for non-cyclic states. And for these, you really need to use the semi-principal theory, or you can use this frame approach. And so let me also repeat the advantages of this. So again, we had an approach independent of the Hamiltonian. So in particular, we did not have to consider the symmetry of the Hamiltonian. And we found that Eik gives you a natural home for the quantum geometric tensor because it is related to covariant derivatives. So with that, I want to thank you for your attention. I'll be happy to answer any questions you have. Thank you.
Thank you very much.
Thank you, Eric.
Questions, comments? I have one. Your Hamiltonians do not depend explicitly on time, right?
No, they differ, they become time dependent when you change the system parameters, or you can use the same spaces and just insert a time dependent Hamiltonian. That's also possible.
Then the question is, what are the adiabatic eigenstates?
In the case it is time dependent.
Yes.
Well, if you just have a time dependent, of if your Hamiltonian just depends on time, there are no system parameters, then your Hamiltonian defines a path in NV. At least I assume that the Hamiltonian is constantly non-degenerate. So if you just say, okay, I have time dependent Hamiltonian, then the Hamiltonian is a path in NV.
Yeah, abstractly, but
Yes.
the background of my question is, in that scenario, the eigenstates of your Hamiltonian are not the eigenstates of the energy eigenstates. That's different for non-Hermitian Hamiltonians. And usually you would expand in the energy eigenstate eigenvectors in the Hermitian case, no? So what would you expand in that case?
So you mean there are two different kinds of
Yes, they're not identical in that case.
Oh, then is this also of finite dimensions?
Yes, it's finite dimensions, infinite dimension, doesn't matter.
So I was like, well, like an eigenstate is just defined by this condition. So so which of the two classes is that, and how do you define the other one?
Well, that's my question. Which one do you choose?
Well, I'm amazed that there are two different, like to me,
Yeah.
like eigenstate that just go to linear algebra 101, like the eigenstate of a operator or a matrix, and that's what I'm constantly using.
Okay.
It's because, well, if you have h of t, then the relevant fiber at time t is just, well, all eigenvectors of h of t. So if you would write h of t as a matrix, you just find its eigenvectors, and these are then the eigenstates. At least that's what's appearing here.
Okay. Thank you. And any more questions, comments?
Yeah, I have a simple question concerning the last slide where you said these geometric non-Hermitian geometric phases do not depend on the symmetry of the Hamiltonian. Are you saying that real asymmetric Hamiltonian or real asymmetric matrices, as well as complex non-Hermitian matrices, would have the same singularities? I wouldn't be able to tell them apart?
No, sorry. I think there's a subtle thing going on here. So our approach to them, that is independent of the symmetry of the Hamiltonian. So you get the spaces like spec h, Eig h, just, well, that's the same for everything. But if you know a symmetry of the Hamiltonian, then you can reduce the spaces. So then you will know that, for example, if the Hamiltonian is always Hermitian, then you can show that spec h is trivial, for example. And then you know that there will be no exceptional points, etc.
Okay, thank you.
More comments, more questions? If not, we had a lot of questions, then let's thank Eric again. Thank you very much, Eric.
Thank you, Eric.
So